Hey everyone, welcome to my channel. In this video, we will study about Carnot heat engine. First, we will see what is a heat engine. Heat engine is a cyclic device which converts heat taken from the source into mechanical work. And Carnot heat engine is a type of heat engine which works on the basis of Carnot cycle. And the Carnot heat engine also gives the efficiency of a heat engine. Now first we will see the Carnot cycle. For studying the Carnot cycle, we need a cylinder with perfectly insulated walls but perfectly conducting base. For example, if we have a cylinder like this, then its walls should be insulated, perfectly insulated, but its base should be conducting, and it should be closed with a tight fitting, perfectly insulated, frictionless piston. Now the piston which we will apply here should be frictionless and it should be insulating. Why should it be frictionless? Because if there will be friction in the piston, then some of the heat will be wasted. Now also the cylinder should be filled with the fixed mass of a perfect gas which will act as a working substance. Now then we need a hot body which has infinitely large heat capacity, okay, and it will act as a source. The hot body with infinite heat capacity will act as a source, and then we need a cold body which also has infinite heat capacity and it acts as sink. The temperature at the source will be T1 and temperature at sink will be T2. Then we can also require a perfectly heat insulating stand. Now the Carnot cycle is shown here. Here is the source which is at temperature T1. Suppose Q1 heat is given to the working substance. Here is the working substance, and the Q2 is the heat which is taken out from the working substance, and here it is the sink which has temperature T2. Now a PV diagram of Carnot cycle is shown here. We will discuss it now step by step. At first, the working substance is connected to the source at temperature T1. Now the first process in Carnot cycle is reversible isothermal expansion, which is shown here in the PV diagram from A to B. This is reversible isothermal expansion. In this, the delta U is equal to 0, means change in internal energy in reversible isothermal expansion is equal to 0. Now we will consider that let Q1 be the heat flown from reservoir into gas, means let Q1 be the heat which we will take from source into the gas, which is the working substance. The perfect gas here is the working substance. Now work done by the gas on surrounding will be equal to W1 equal to integration from A to B. Since we are taking our gas from A to B, there is a isothermal expansion from point A to B. So W1 will be equal to integration, limits will be A to B, P into V. Since we know that work is equal to P, dW is equal to P dV. So on getting the whole work, we will integrate it from A to B. And since we know that according to first law of thermodynamics, dq is equal to du plus dw. Here du is equal to 0, as already we have told that du is equal to 0. So our heat flown from reservoir into gas will be equal to the work done by the gas on surroundings. So work done will be equal to, here we will replace P equal to nRT by V, as we know that PV is equal to nRT. From here we have taken the value of P. From here we have taken the value of P. So value of P is nRT upon V. Here we have substituted this value of P in this P value. So here temperature is T1. So it will become nR T1 upon V dV. Now integrating this dV by V in limits a to b, we will get log Vb by Va. So the work done by the gas in isothermal expansion, reversible isothermal expansion is equal to W1 equal to nRT1 log Vb by Va. Now our second process will be reversible adiabatic expansion, which is shown in the PV diagram by the points B to C. This occurs from point B to C. This is PV diagram. Okay. In this process, the T1 changes to T2 in reversible isothermal expansion. At that time, temperature was constant. Temperature was not changing. But in reversible adiabatic expansion, our temperature is changing from T1 to T2. Now, work done by gas will be equal to B to C, limits of integration and P dV. Now, we know that for adiabatic expansion, we can write PV raised to power gamma is equal to a constant. We know this formula that PV raised to power gamma is equal to a constant. Then we will substitute P value from here. P is equal to K by V gamma, V raised to power gamma. Then on solving this integration, we will get K upon 1 minus gamma, 1 upon V raised to power gamma minus 1 minus V gamma minus 1. How we have solved this integration? We had B to C, V raised to minus gamma dV. On integrating, we got V minus gamma plus 1 upon minus gamma plus 1. And the limits were B to C. So we have just substituted the values of C and B limits here, and we got this value. Now we know using this relation again, we can substitute value of K. So we can substitute in the here we can substitute PC Vc raised to power gamma minus PB Vb raised to power gamma. And now we know that PV is equal to nRT. So from here we will substitute the value of P nRT upon V. As I've shown here, we have substituted the value of P here. So after this gamma will be cancelled with this Vc gamma, and Vc will be cancelled by minus Vc raised to power minus 1. So after solving this, we will get V2 equal to nR upon 1 minus gamma T1 minus T2. Here n is the number of moles. Now again rearranging the negative terms, we will write nR upon gamma minus 1 T2 minus T1. We have taken minus common here, so we will get nR upon gamma minus 1 T2 minus T1. This is the work done by gas in reversible adiabatic expansion. Now the gas is at relatively low temperature. As here we can see that earlier the pressure was here. Now at C point a pressure is lowered, so we have to compress the gas to regain its initial state, and we can do this compression in two ways: isothermal expansion and adiabatic compression. Isothermal compression and adiabatic compression. Now cylinder is placed in contact with cold reservoir, that is sink. Earlier we connected it, we put it contact in the source, but now we will place it in the contact with the sink. Now the reversible isothermal compression is shown by the curve C to D. Here Q2, we will consider that Q2 is heat given by the gas to cold reservoir. Since we are compressing it, so we will consider that Q2 is a heat given by gas to cold reservoir. So work done in this process will be equal to Q2, because in isothermal compression delta U is equal to 0, change in internal energy will be equal to 0. So work done will be equal to heat. So as we solved it in reversible isothermal expansion, similarly we will get the formula nRT2 log Vd by Vc. Here Vd is less than Vc. This will imply that W3 will be negative. That is, our value of W3 will be minus nRT2 log Vd by Vc. We can write it as W3 equal to nRT log Vc by Vd. Now a fourth process will be reversible adiabatic compression. A fourth process is shown here, D2A. This is the reversible adiabatic compression. Here now delta Q equal to 0. In adiabatic compression, change in heat will be 0. So the work done will be equal to D2A limits P dV, and similarly as we got the value of work done in this reversible adiabatic expansion, similarly we will get the value of work done here also, which will be Nr upon gamma minus 1 T2 minus T1. Now from this equation and this equation we can conclude that W4 is equal to minus of W2. So as we can, if we take minus 1 common here, it will become minus Nr upon gamma minus 1 and T1 minus T2. So we can write it as W4 equal to minus W2, since the value of W2 is Nr upon 1 minus gamma T1 minus T2. This can be further solved by 1 minus gamma. Then since T2 is less than T1 here, we are compressing the gas, so temperature will be less here. T2 will be less than T1, so W4 will be negative, because here we are getting T2 is less than T1, so W4 will be negative. Now here we can conclude that in Carnot cycle we are extracting heat Q1 from source at temperature T1, and we are putting back the heat Q2 in sink T2. So total work will be equal to W1 plus W2 plus W3 plus W4. Now as here I have shown that W4 is equal to minus W2, so we can write W1 plus W2 plus W3 minus W2. This will get cancelled, and also here I have shown that W3 is negative, so we will write W1 minus W3. So on putting the values of W1 and W3, we will get this equation: nRT1 log Vb by Va minus nRT2 log Vd by Vc. Now we know that Tv raised to power gamma minus 1 is a constant, so we can write T1 Vb raised to power gamma minus 1, T2 Vc raised to power gamma minus 1. Now taking this T2 this side, we will get this equation, and similarly we will do for D and A state also, and we will get T1 upon T2 equal to Vd upon Va whole raised to gamma minus 1. Now on comparing these two equations, we will further get this value, and then we can conclude from here the bars will get cancelled, and we will get Vc upon Vb equal to Vd upon Va, and on further arranging the terms we will get Vb upon Va equal to Vc upon Vd. So total work done, as here we have given that total work done was nRT1 log Vb by Va minus nRT2 log Vd by Vc. Now these two terms have become same, log Vb by Va, so we can take it common, and here Vc upon Vd is equal to Vb by Va, so we can interchange these two terms. Vd will become Vc and Vc will become Vd, and here we will change the sign. So log Vb by Va will be taken common, and the other term will become nRT1 minus T2. So efficiency, as the Carnot heat engine is used to give the efficiency of heat engine, so we can find the efficiency by this formula: eta is equal to W upon Q1. Now we know that W is equal to Q1 minus Q2 upon Q1, and here we can write that after solving this we can write 1 minus Q2 upon Q1. Also we can write the formulas which we have derived here: W upon Q1, value of W1 is equal to nR T1 minus T2 log Vb by Va, and value of Q1 was nR T1 log Vb by Va. This will get cancelled, nR will also get cancelled, and we will get W by Q1 equal to T1 minus T2 upon T1. On solving this we will get 1 minus T2 upon T1. So this is also the efficiency. Now on comparing these two equations, we will get T2 upon T1 equal to Q2 upon Q1, as 1 minus Q2 upon Q1 is equal to 1 minus T2 upon T1. This one will get cancelled, minus sign will also get cancelled. So T2 upon T1 will be equal to Q2 upon Q1, or we can write that T1 upon T2 is equal to Q1 upon Q2. So for ideal gas, we conclude that Q1 upon Q2 will also always depend on T1 and T2. And also we have found out this efficiency of the Carnot heat engine.